Okay, HR diagrams. HR stands for Hertzsprung-Russell. Hertzsprung-Russell are two gentlemen that came up with this diagram. They were German. That's the HR, because it's easier to say HR than Hertzsprung-Russell
Diagram.
Every time I try to say it with a German accent, it comes out in a Scottish accent, which is hilarious because I can speak German with a German accent, and I don't know anything about the Scots. So there you go. Okay, on the HR diagram, you guys can stop talking, pay attention, okay? You will notice some things. The first thing you should notice is that it's set up a little differently than most graphs. This graph, okay, over here we have luminosity. What does luminosity mean, Brendan?
How bright it is.
How bright something is. We measure light bulbs in the room on how many lumens they emit, or how much light is emitted. Well, they're also measured in how much power they use in watts. But an incandescent bulb that's the same wattage as a fluorescent bulb will put out a different amount of lumens, which is the amount of light that's actually being produced. Okay. Luminosity is how bright something is. I would write that down. That would be really helpful in understanding this stuff. Okay, how bright something is.
It's very bright.
All luminosity, all magnitude of stars is based off of which star?
Sun.
Our sun. Okay, it's all related back to our sun. So if you look on your HR diagram, you'll see 10 to the negative 4, negative 2, 1, 10 to the 2, 10 to the 4, 10 to the 6. Okay? 1. What is the luminosity of our sun? 1. So this is 10 to the 2 times more bright than our sun, or 10 to the 4 times more bright than our sun. Yeah, it could be 3, but 3 would be here.
Yeah, but they don't have that.
Oh, not on this particular chart. Or you could have 10 to the negative 2 or 10 to the negative 4 times less bright than our sun. Okay? So our sun would be somewhere here, in here somewhere. Our sun has a temperature of around approximately 6,000 Kelvin, somewhere in there. And we'll note on our temperature scale here, between 40,000, 20,000, 10,000, 5,000, 2,500 Kelvin, you don't say degrees Kelvin, you say how many Kelvin. So if we take about 6,000 Kelvin, go up to about 1, that puts our star somewhere in here. Okay, our star is pretty average. Works for us. It puts out just enough radiation that we can feel warmth and enjoyment and life and happiness, and everything lives, but not too much harsh radiation that we all die from crazy waves of nastiness. Okay, so gamma rays, X-rays, and all of that stuff. Yeah?
So what happened if our sun was like the temperature was 10
If our sun's temperature was 10,000, well, the first thing that would happen... What, these things? Okay.
So the temperature, the luminosity thing, what if it was like where the supergiant thing?
The supergiants?
Yeah.
It would be very bright on Earth. Okay?
Wouldn't it wait?
Well, yeah, it would, but not all bright stars are supergiants. Okay, so this is where our sun is. It is approximately 6,000 Kelvin in there somewhere. It is 1 on the luminosity scale. Now what's important is on your handout, I made a mistake. So I set up the temperature scale wrong compared to where the planets were. So it said our sun was a blue star. Is our sun a blue star?
No.
No, look at the sky. What color is it?
Look
What color is our sun?
Yellow.
It's yellow. It's yellow. Our sun is a yellow star. Okay.
Also, wasn't there something on the top left, like above the main section
Okay.
on our graph?
Yeah, there was. It was the blue giants. They don't always show up. Yeah.
So the sun's going to be in for the rest of the other stars.
Yeah, our sun just happens to be average. This is
No,
the data we
median.
take.
We want to like,
The median,
yeah, we want to take it.
median, average, and then the same thing.
Yeah.
Well, median, a point, and
We have median, mode, and
Yeah, mode is average, median.
I'll talk about average.
okay. Our sun is right here. This is what you need to know. Yeah, Chris.
So what were we saying about if it was 10,000 Kelvin?
Okay. Shh. Listen up. If our sun was 10,000 Kelvin, it would no longer be a yellow star. It would be a greenish bluish star. It would put out a different color of light. We would see it differently in the sky, which would be really cool. But it would also be putting out a lot more energy because it's that much hotter. That Earth would have to be a lot further back from the from that sun, or we wouldn't be in that Goldilocks zone where the water is liquid and not frozen or evaporating, or we're not burning up. Blah blah blah. Okay, this is HR diagram. Now we find that most stars fall on the main sequence. Most stars, the vast majority of stars that we see in the night sky that we can measure, are on the main sequence. Okay? And we have the white dwarfs down here. We talked about this yesterday, so you should know that a white dwarf is a star that is not cold. Look where it is here. It's very hot, but it's also very dim. Okay? Very hot, very dim. That's good to know because you know that temperature does not determine brightness, luminosity. Okay? Brightness is more a factor of how big, size-wise, the star is. Because here we have these supergiants. Well, this is red. Red, 2,500 Kelvin. Very kind of a colder star, so to speak. It's still toasty hot. It's a star. But a cooler star is red, but it's very bright because it's expanded and has more surface area. More light can escape from the core, and it's very, very bright. A good example would be Betelgeuse, or if you say it in the proper German, Betelgeuse. Okay, this is the HR diagram. We looked at this yesterday. Okay, what else? Okay, a lot of you guys asked about this magnitude issue. This is very simple. Apparent magnitude, if you're standing on Earth and looking at different stars, especially our sun, it's pretty darn bright. Okay? Why is our sun so bright on Earth?
Because we're really close to it.
We're really close to it. We're really close to it. Not all stars are going to appear as bright as they do on Earth. So they came up with a system of trying to quantifying how bright different stars are viewed from a set distance. So our sun from a set distance would have an absolute magnitude of something. It's on the chart next. As compared to Betelgeuse or Sirius or Arcturus or Vega, or all these different stars have different absolute magnitudes. So this is a way to quantify what actual brightness does it have if we view all of them from 32 light years away. Pretty simple. Absolute magnitude. How bright is the star? We're not really going to get into the complexities of this. This is something, just understand, absolute magnitude is how bright is the star. Chris?
So, apparent magnitude is how bright the stars are.
Yeah, apparent magnitude is how bright it is at Earth. You don't really even need to write this down. What you need to know is absolute magnitude. Okay? Absolute magnitude is how bright is the star compared to other stars. So what you should be writing down is absolute magnitude is the brightness of a star compared to other stars from a distance. Done. So if I said, what's the absolute magnitude of a star mean? You're going to say, it's how bright the star is. Julius, what does absolute magnitude mean?
The apparent brightness of the star.
There we go, how bright a star is. Okay? Oops. So this would be, if you want to look on the notes, you go online, look at the notes. Okay, this is our sun. Yeah, light years away. We're 8 light minutes away from the sun. Okay, apparent magnitudes as compared to the absolute magnitudes. You can see they change what it would look like on Earth. So these are the numbers that we're going with. Not really that big of a deal. You should know that some stars in the sky on Earth are brighter than other stars because they're closer to us or they have more luminosity. Okay. The Hertzsprung-Russell diagram shows the relationship between absolute magnitude and temperature. Absolute magnitude, we can also call it, starts with an L, luminosity, how luminous, how bright it is. So absolute magnitude, luminosity, brightness, and temperature of the stars. We know this, we talked about this, we did the worksheet. Main sequence star. Okay, I'm going to briefly talk about the different sections of stars on the HR diagram. We're going to start out with main sequence. Okay, the vast majority of stars are in the main sequence. What did we say when we were doing stellar evolution on what is a star fusing in the main sequence?
Hydrogen.
Hydrogen. Stars in the main sequence fuse hydrogen. How long of their lifespan is spent in the main sequence?
90%.
90%. Approximately. 90% of their life. So here we have a different version of the HR diagram. Now, one of the reasons I like this one is because it shows that the higher you go in your absolute magnitude, what happens to the surface size of the star? Not hotter, the size of the star.
Is it expanding?
Yeah, it's expanding, it's getting bigger and bigger. So down here we have these little bitty tiny little stars that are very dim. Very, very dim. And as we go up, we see that the stars get bigger and bigger. So even in the main sequence, all of these stars are fusing hydrogen. They're all different stars. This star doesn't actually move this way. Our sun's not moving this direction. This is just where our sun is. Done. Pointed there. Other stars, as you get up towards these really big, massive blue stars, are just bigger, hotter, and they're brighter because they are bigger in size. You have the supergiants that have swollen because they're no longer fusing hydrogen anymore. Now they're fusing everything else. They're swollen, and because they have more surface area, there's more of the star to see. More light can escape. Thus, it's brighter. And then down here we have the white dwarfs, which are really, really small. It's the core of these stars. But they're very hot, but very dim because of how small they are. You guys seeing the relationships here?
So size is what determines luminosity?
Typically, yeah. So as we go up, we have much. Oh, okay. Size determines luminosity. I'll go with that. That's simple. We can make it simple. Okay. Scott, you get that? Scott, what determines how bright a star is? Size, good. That's you're paying attention. Okay, alright, so that's the main sequence. Then we have the red giant stage and super red giant stage. We've talked about this. We know that red giants are no longer fusing hydrogen. What are they fusing? Other elements. That's a great thing. It starts with helium. You know, 2 heliums make a 4. That's beryllium. Then you can get some boron, some carbon, some oxygen, some nitrogen, some fluorine, right? Neon. All these different elements up to the element iron. And at iron, it stops. No more after iron. Once it starts fusing iron, it collapses and dies. Will our sun ever get to iron?
No.
No. Our sun might get to carbon. Okay, and then it's just going to fizzle out and become white dwarf. Sean?
Why is lost I don't know, periodic table? Why are those other ones?
I'm sorry, say that again?
You say it stops at iron. Why is there other elements on the periodic table?
Ah. The reason there's other elements on the periodic table is that when it stops at iron and collapses and explodes, it gets even more hot, and the explosion intensity starts to fuse other things together. So, what we call the iron barrier, that iron barrier is breached in the supernova itself. So the supernova itself releases so much energy. It's brighter than an entire galaxy. when it goes off. So that's in that explosion, when everything's being ripped apart, everything starts getting fused together crazily during the explosion, and you get super bright, super intense. And that's where you're getting the golds and the leads and the mercuries and all the heavier elements. Okay, so the red giant stage, large cool star, okay, it's in the upper right. Supergiant, very large cool star, upper right. Okay, there's some other stuff on here. You don't really need to know this as far as memorize this, but I think it's good to know that stars are not the only thing that glow in space. You also have nebulas that glow. You have emission nebulas, reflection nebulas, then you have nebulas that don't glow, dark nebulas. Nebulous cloud of gas in space. It can glow either because it has its own heat, or because there's a star behind it, or it's getting reflected. But nebulas glow in space. They're really cool. Okay, so here would be a nebula. This is the Horsehead Nebula. I forget what kind, if this is emission or reflection. It's a glowing nebula. That's all you really need to know. That's kind of cool. And what happens in nebulas? What was that? Creation of stars. Yeah, the creation of stars. What do we call that theory of the creation of stars? Solar nebula theory. Very good. So, we're just about done here. This was going to take very little time today. Our star starts out as a main sequence star. Okay? As it starts to die, 90% of its life is gone. Most of the hydrogen is gone. It starts to fuse helium. It swells and goes through stages of giant life. On the diagram, it will get bigger as it starts to fuse heavier and heavier things, and eventually it will fizzle out and die. You get the planetary nebula, it turns into white dwarf. Black dwarf, the light goes out.
What's happening to the stars?
Is that?
There's no more fusion. It's just stopped.
Oh, it went from white dwarf to black dwarf?
Yeah.
Yeah, it's just all the energy is spent, but it's stable, so gravity can't hold on to it because it's so solid, so small. So it just goes out.
So how do we see those when they happen?
To my knowledge, these are theoretical and we cannot see them. Brendan.
If the whole red giant stage happened and it went into white dwarf stage, would we be able to like find out if we could have life on Mars? Since
Life on what?
Life on Mars. If the red giant stage didn't destroy us and swell up too big.
Well, when our sun goes red giant, it will swell almost to Mars,
Yeah.
and then Mars would no longer be in the Goldilocks zone if it even survived, which I don't think it will. So, and to answer your question, if our sun goes red giant, everything dies.
Yeah, but if that would just skip. If we were like just went to white dwarf stage, which wouldn't happen, but wouldn't be able to like live on Mars.
White dwarf? No,
Well, yeah.
because the sun would be too dim.
Oh.
Mars would get too cold where it would stay outside the Goldilocks zone.
Oh.
Okay. Okay. We talked about galaxies in here? We did. So just a quick refresher. What kind of galaxy is this?
Irregular.
Not an irregular.
It's like a
That's the irregular.
That's the regular.
This is
Elliptical.
elliptical. So this one's the elliptical.
Yeah,
That's
Okay,
fine.
what kind of stars are in the elliptical?
that's later. It's like an escalator.
What kind of stars? Are they old, young?
They're
Oh.
They're old. So these are old stars. These are old stars. These are often the cores of galaxies. So if we walk over here, you can see these little circles here in the middle are elliptical shaped, and they're surrounded by these falling pins. They're surrounded by these bands. What are these? They're spiral galaxies. What is the core made of?
elliptical.
Old elliptical galaxies, right? Old stars.
And they spin.
And what are this bands and spirals? What are they?
Young stars.
Yeah.
They're what? Yeah, they are stars, but what kind of stars?
No.
They're young stars, and they have a lot of,
And
starts with an N,
nitrogen.
nebulas. Nebula. So lots of clouds of gas and dust here. These are spiral, and they're younger stars in the arms. Okay, well what's going on with this guy? Okay, it's the irregular, that's good. Irregular. So this would be similar to having these spiral-shaped arms, but without a core for all that to rotate or orbit around, revolve around, so they don't get those nice spiral shapes, they just get these weird funky shapes. So if they're made of spiral arms, what kind of stars are they? What was that? You don't know, huh? Was that? If these stars in nebula are the same kind of stars in nebula we see in the spiral arms of a spiral galaxy, what kind of stars are they?
Young.
They're young. Okay. And again, for posterity, what is the name of our galaxy and what kind of galaxy is it?
Milky
Way.
It's a Milky Way, it's a spiral. Here, because these are weird. You can see galaxies crash into each other, which is cool when you get those pictures. You can see stuff like this where it looks like it's all been ripped apart in the past. There's a lot of different kinds of elliptical galaxies, and I don't think the two look the same. Okay, so we have the Milky Way galaxy. Okay, our Milky Way is pretty darn big. It's 100,000 light years long, but it's only about 10,000 light years thick. Brendan, what's your question?
Isn't there a galaxy that is like about the same as the Milky Way?
Yeah, a lot of them. Yeah, Milky Way is just a spiral galaxy. Our closest spiral galaxy is the Andromeda galaxy. It's also a spiral, so it looks a lot like ours.
Have we seen inside yet? Operating.
Have we seen inside the what?
No, that galaxy's next cloud.
I'm not sure. I know it's harder because they're so far away. We can see into our Milky Way. This is what the Milky Way looks at from the side. And this is why the Milky Way is called the Milky Way. If you look in the night sky, you see this white streak across the sky if you can get away from all the light pollution. And you'll see all that concentrated mass of stars in the distance. That is the Milky Way. And our Milky Way is a spiral galaxy. Obviously, we did not take a picture of this because we're in it. This is more of a picture of our Milky Way. Brendan.
How do we see what the Milky Way looks like from inside of it?
Radio telescopes can give us information and we can extrapolate what it looks like based on the data we get from different wavelengths.
It's crazy.
It is crazy.
Is
Is
it
that a
like,
hand over there? Friend?
is it like the ocean, like how we see, because Miss Lindemann, she was talking about how like we see the ocean by sending like radio lengths and when they bounce back.
She's talking about radar and sonar.
Yeah.
This is more just watching what's coming in. So it's a radar telescope. So instead of sending out radar signals, it's just collecting radar signals. Okay? We talked about spirals, we talked about ellipticals, so check the notes. I don't want to belabor this. Look, spiral galaxies. Woo! Elliptical galaxies. Irregular galaxies. Did I talk about galaxy clusters?
Oh,
No.
A galaxy cluster? Guess what that is?
A
A cluster of galaxies. Sometimes you get, this is an irregular galaxy. Here's a galaxy cluster. So here we have spiral, 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 elliptical, maybe two ellipticals and some other ellipticals, where these galaxies are all grouped together now. Together means they're kind of close to each other by hundreds and thousands of light years. However, they're not exactly touching each other. Right? They're kind of clustered together, and then way over here, there's nothing. It's just space. Very powerful telescope called Hubble. Okay, and we've talked about that a light year is a measure of
Distance.
distance. That's all I have for you today. All right.